Question 4. State the principle of superposition. Now, there's nothing to explain here. It is simple. It says when two or more waves meet, their resultant displacement is the sum of the individual displacements. It's as simple as that. Then B. Coherent light is incident normally on two identical slits. So look at the two slits, this slit and this slit. There is light which is coherent, which is coming. It's incident normally, meaning that it is coming like this and the slits are like that. So there is 90 degrees between the two. It's incident normally on two identical slits, X and Y. The diffracted light emerging from the slits superposes to produce an interference pattern. So light, what happens, what they're explaining is they're actually explaining the process that happens when the light passes through the slits. They are saying that the diffracted light through the slits, yes, light is diffracted when it passes through the slits. So that's the diffraction. When light enters here, then it is spread out like that. Then another light entering through these slits, it is diffracted like that. So when this light meets now, that's when there's going to be, because it is diffracted into each other's region. So by being diffracted into each other's region, this light meets, and when it meets, it produces an interference pattern, as the question is saying. So the diffracted here, the diffracted light emerging from the slits superposes meaning that this light meets and the resultant displacement will be equal to the sum of the individual displacements of the waves. And an interference pattern is on a screen positioned at a distance from this one. So we have an interference fringe pattern being observed. As you can see, we have a dark fringe here, dark, 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 dark. So a bright in between. So a bright fringe, bright fringe, bright fringe, bright fringe, bright fringe. That is what is called an interference pattern. So an interference pattern is that what we saw here, dark, bright fringes. Okay, so the separation of the slits is 0.65. The separation of the slits is 0.65. I think this is clearly written here. The separation of the slits is 0.65. The distance between the centers of adjacent bright fringes is 1.7 millimeters. But before we go further, this also is equal to A. A is the slit separation. Now we are told that the separation, the distance between centers of adjacent bright fringes is 1.7 millimeters. So centers of adjacent means next to each other's bright fringes. Center of the bright fringe, center of the bright fringe, and they are adjacent because they are side by side like that. It's 1.7 millimeters, like that. Okay, and this is given the label X. Then calculate the wavelength lambda of the light. So you're given this data. You're also given this one, which is D, capital letter D. So we write our formula here. The formula says X, the double slit experiment formula. X is equal to lambda D over A, which, since we are looking for wavelength, we multiply both sides by A here. Then we divide both sides by D. This gives us lambda equals to lambda AX over D. We have A is 0.65 millimeters, so we have to change it to meters, so we multiply by 10 to the power of minus 3. We have X on the numerator there, it's 1.7 millimeters, so it has to be multiplied by 10 to the power of minus 3 to change it to meters. Then we divide it by D, which is in meters. So this gives us 5.8 times 10 to the power of minus 7. That's our wavelength there. The next part of the question. Light waves from slits X and Y in B arrive at a point between adjacent bright fringes on the screen. Light waves from slits X and Y. Light waves from slits X and Y. So the light which are coming from slit X and slit Y in B arrive at a point between adjacent bright fringes. So at some point between adjacent bright fringes. So for example, we are saying that the point can be anywhere here. At some point between adjacent fringes, if these are adjacent bright fringes, there is points in between here. So at some point between those adjacent bright fringes. Why are they saying so? Just to give you an explanation. The point is this. At the center of the bright fringe here, light will arrive in first. At the center here, light will arrive in first. At the center here, where there is a dark fringe, light arrives antiphase. So antiphase means that the first difference is 180, 540, or the likes. In fact, we can say antiphase. We can just come and say, okay, antiphase, we can find the first difference by saying n plus of times 3/6, the first difference, if it's antiphase, which produces destructive interference, which produces the dark fringe. That will be the first difference in degrees here, where n starts from 0, 1, 2, going like that. But in phase, where there's a bright fringe, the phase difference will be n 3/6 like that. And n starts from 0, 1, 2, continuously like that. So here, the first difference is going to be 3/6. Obviously, it's 360 because then n will be 1, because it's after one adjacent distance. So the first difference is 360. Now, of the waves arriving at this point and at this point, okay. So even if we are not going to worry about this too much, my point is more related in the fact of what about the first difference of waves meeting here? Because for there to be, let's say, a pattern there, waves must come from here to here, meeting at this point. So when they meet at this point, the waves are meeting with the first difference, which is not, let's say, 180, as will be produced by this equation, or 360, or 0, as will be produced by this equation. So the first difference is going to be less. So that's what the point is indicating here by saying light waves from slits X and Y in B arrive at a point between adjacent bright fringes. So at some point in between on the screen. Fig 4.2 shows the variation of the displacement with the time of the waves arriving at the point where they meet. So the waves arriving at that particular point, this graph here shows the two waves with the time, how they vary with the time, how their displacement varies with time at that particular point between the two bright fringes. A student makes two statements about the waves at this point. Statement 1, the first difference between the waves is 90 degrees. Statement 2, the amplitude of the resultant wave is 0. Explain how statement 1 is correct. Now, statement 1 is correct in the sense like this. How do I know that statement 1 is correct? Because of this. First difference can be calculated, but first difference can also be observed from the graph. For example, take this. When this graph here is at the maximum, this one is at 0. Right? This one at 0, this one at maximum. Check out carefully. Okay? This one at 0, this other one at maximum. So this one at 0, this other one at maximum. So considering that the waves are coherent, I mean that the constant phase difference, and also it means that they have the same frequency and the same wavelength, considering that they have the same wavelength. So the question is, how do we then judge the wavelength? How do we obtain the wavelength? The best way is to find the distance between two successive crests. For example, take out this crest here, this crest here, okay, the other crest of the other wave, like that. Now we want to know what that distance is in terms of wavelength or in terms of period. It is clear if you check out carefully that from here to here, according to this wave X here, that's a quarter of a period. So when the crest, this one happens, it happens a quarter of a period after this crest has happened. So using the formula for first difference, we can say that 360 360 t over period. So we know that t, the time taken for this wave to have its own crest after this wave x has its own crest, it's a quarter of a period. So if it's a quarter of a period, then we say right here 1/4 t over t. T and t cancels. 1/4 of 360 is 90 degrees. So the first difference between the two waves is 90 degrees. So explain how the statement is correct. The waves are out of phase by a quarter of a cycle. That's the truth, actually. Yes. What does it mean out of phase by a quarter of a cycle? It means that wave y has its own crest after a quarter of a cycle, a quarter of a cycle later after wave x has its own crest. And we proved it there. It's a quarter of a period, a quarter of a cycle. So a cycle has 360 degrees. So therefore, a quarter of a cycle will be 90 degrees. State and explain whether statement 2 is correct. So in statement 2 now we must establish whether it is correct or incorrect. And based on that establishment, then we have to explain whether it is correct or incorrect. So we have to state whether it is correct or incorrect, then explain why it is correct or incorrect. Now, what does statement 2 say? Statement 2 says that the amplitude of the resultant wave is 0. So the resultant of these two waves, the amplitude is 0. So we have to check. Now we don't even need to check a lot of places. Take, for example, the resultant of these two waves. This wave, which I have circled there, its displacement at this particular instant is 0. This one, its displacement is not 0. So adding these two, the resultant wave cannot have an amplitude of 0. Having an amplitude of 0 implies that at every point, the resultant is 0 at every point. Now, this is proven that even at the start here, the resultant is not 0. Even if we use this point here, here there is a displacement, here the displacement is 0. Adding these two will not give us a resultant of 0. So there is no chance that the amplitude is the maximum displacement, or the maximum total displacement. So if the total displacements are already greater than 0, then there is no way the maximum total displacement can be 0 at any point. So this statement is incorrect. Why is it incorrect? It is not correct because the displacement of the waves are not always equal and opposite so as to completely cancel. So if we wanted them to completely cancel, we must have waves which are equal, number one, and always opposite, such that, for example, if this one is equal, has a magnitude of 3 in this direction, which will be -3, and this one has a magnitude of 3, they will cancel out and they are equal, always equal and opposite in direction. So that's not the case here. The case in this wave is that they are not always equal and opposite in direction. So there is no chance of us saying that the amplitude is 0 at all points. Then the final question D, the width of each slit in B is decreased by the same amount. So the width of each slit in B is decreased by the same amount. There is no change to the separation of the slits. So the slits are not changed, their separation. The width of each slit in B is decreased by the same amount, but there is no change in the separation of the slits. Describe and explain the effect, if any, of this change in the appearance of the interference pattern. So there is no change in the separation of the slits. So we are still using the same wave just to prove the point. X is lambda d, remember, over A. If this is unchanged, because there is no change in the slit separation, then D is unchanged. We still have the same distance between the screen and the slit. Lambda is unchanged. We are still using the same wave. Then fringe separation will also be unchanged. Now the question is, so what is happening here? The width of the slits are decreased. Now you must know that when you decrease a slit, there's going to be more diffraction. For these slits, probably the diffraction was like that, but for smaller slits, there's even more diffraction. More diffraction means that the wave is now going into even more regions where the wave was not originally going. So it has an effect. The first effect is that if the wave is spreading out more, obviously its intensity decreases. What do I mean here by intensity? Its intensity decreases because if the wave is spreading out more, then it means that it is reaching more areas. If it is reaching more areas, then the energy is spreading out to more regions, which means that if you are going to look for intensity, remember it's power per unit area. So the power arriving per unit area is going to be less because the power is being spread into many areas. So per unit area is going to be less. So the intensity is going to be less. So if intensity is going to be less, but remember that for bright fringes to form, constructive interference must happen. And when constructive interference happens, then we have a bright fringe with brightness, high intensity, because the amplitudes have joined. But now if intensity has decreased, it means that the waves that are meeting, they are meeting with lesser intensity, with lesser amplitudes. So the amplitudes or the displacement that adds are less. And if they are less, then they produce a less resultant, which will produce a less intensity. So our fringes on the screen will be less bright. Our bright fringes will be less bright. So that is an effect, if any. That's one of the effects that I am explaining here. The bright fringes will be less bright. Remember, we are supposed to describe and explain. So the bright fringes will be less bright. I didn't write that answer particularly here. Since the wave is spread out more due to more diffraction when the slits are less in width. That's the explanation for that. Now there's another answer also. The fact, of course, the fringes may be less bright, but remember that the fringes are formed when there's interference between the diffracted waves. Now imagine if the diffracted waves were covering a region of, let's say, 1 meter. So our fringes will all be in that 1 meter. The destructive and constructive interference will be in that 1 meter. But if the diffracted waves are now covering, let's say, 3 meters, it means that we are going to have fringes in a region of 3 meters. So, and considering that the distance, fringe separation X has not changed, the distance between successive bright fringes has not changed. It means that in 3 meters, we have more bright fringes and dark fringes compared to in 1 meter. So that's why I wrote this answer. There is more diffraction, hence there is more fringes. So more fringes is the effect. Then the explanation is because there is no more diffraction. So